Thank you. Thank you for the nice introduction. My name is Andreas Unterweger. I'm with the Center for Secure Energy Informatics, and I will be talking to you today about a project that we did in 2017-2018. So keep in mind, everything that is blockchain related in this talk used to be very different in 2017-2018. So some of the conclusions from back then, or some of the things that we learned back then, might not be 100% applicable now because the world has changed a bit during that time. But there are still some interesting lessons learned. So let's dive into this practical project that we did in 2018. So throughout this summer school, there was already quite a bit of information that you heard about solar panels, PVs, and I think it should be very obvious that in case you install a PV power plant on your home or in a home with multiple parties, that what you get is basically, on the sunny days, you can decrease the power that you draw from the grid. And what you can also do is that you can, if you have a multi-party home, you can split those units. Multi-party home, you can install PV panels, of course, but then the question is who owns them and how is the generated electricity distributed between the participants, between the homeowners, between the renters, whoever is living in that building. So there is, of course, the question how to share the generated electricity in the best possible way. And there are two main things that should be considered. One is that, of course, you want to use as much of the generated power as possible for the whole building. Because if it's not used, at least in Austria, at least back then when the project was started, the reimbursement that you get if you put excess energy into the grid is relatively low, so it's usually better if other participants of the same home can make use of that energy. And of course you want to avoid to have any sort of unused energy, be it by any participants in the home or be it in any other constellation. So you want to avoid daily cost to feed it back into the electrical grid unless it's absolutely necessary. So when we started the project, there was a new law in Austria that came into effect, and this law basically allowed to transfer energy between two parties in a multi-party home when they had a shared PV, solar, or whatever constellation on the roof. So what was happening is that the law said you can transfer the portion of generated electricity based on prior distribution that the participants needed to agree on. So, for example, you could say you have three participants, A, B, and C, and A has 20% of the generated electricity, B has 20, and C has 60. Can be any other way, of course, just the parties need to agree once. And then the new law said that the participants can change the distribution anytime they like. Anytime being limited to 15-minute windows, so it cannot be any more fine-grained than 15-minute resolution. And this was something that put the energy providers into a very interesting position, because when they did these things with the power plants, they usually were limited to mail, phone, sometimes email, to record how the proportions are distributed between the participants. And that didn't really scale well. So they were in the position that if they said, if really the participants are coming and they want to change this every 15 minutes for all the PV panels out there, we run into a problem. So we want to see how we can solve that. Of course, the energy provider was legally obliged to accept any valid distribution between the participants. So it was not allowed to question to some extent if, for example, participant C gets all the electricity for some amount of time, because it's purely the decision of the people who agree on what they do with their PV plant. So for the purpose of this talk, let me, for example, introduce a transfer. So the party A that used to have 20% transfers its shares to party B. So for the duration of my talk, let's say between 11 and 12, A doesn't have any shares anymore because it moved all of its shares to party B. And you can see that for this 1 hour slot, it will be like this, that participant B now has 40%, more than they had before, and participant C has still their 60%, nothing changed. This is a very typical scenario if I know, for example, that I will not be at home, but my neighbor will be cooking, so it might make sense if there is a lot of PV generation going on, instead of me not using it and putting it back into the grid, it might be better if my neighbor can use it and save some electricity. Maybe he will be nice enough that in return, when he's not home, he will give me some of his electricity when it's a sunny day. Here's an illustration of what this would look like from the energy provider's point of view. So for the energy provider, they need to basically make a list with 50-minute granularity where they see for this particular PV who has which proportion. So you will see before the talk started, we have 20, 20, 60. Then during the talk, for every 15 minutes time slot, we have 0, 40, 60. And then in the end, because I made a mistake by copy-pasting the lines here, I will correct that. In the presentation, of course, it will go back to 20, 20, 60. So that's the basics of how this worked and what the legal framework looked like. The legal framework was very generic. It didn't really specify how the energy provider would enable the participants to give that information, so they could say, we accept this by email, by phone, or whatever. But as I said, they thought this would not scale. So what they did was that they said, we want to have some prototype, some software prototype that makes it possible for the participants to move their shares around. And it shouldn't be too much effort on the energy provider's side, because it's not feasible on a sunny day to have a call center with 20 people who just need to pick up the phone and shift the proportions around and edit some Excel sheet or whatever. So what our industry partners, which were energy providers, what they wanted to do is they wanted to have a prototype for peer-to-peer energy trading, localized to Austria, because they were Austrian energy providers, and they were mostly concerned with the Austrian law at this point in time. At this time also blockchain was a very big hype. Remember back in 2017 when Bitcoin was at around $20,000, $30,000. It was a different time back then. Everybody wanted to do something with blockchain, so they wanted to learn something about blockchain, so they put this project together where they said, well, maybe blockchain can solve this issue. And we as research partners were interested in seeing if blockchain is maybe an application for that. I will come into the details in one moment to see what speaks for or against using a blockchain in this use case. Because not every use case is absolutely suitable for blockchain, as we all know. So this is something that they wanted to see if it's applicable, and even if they decide blockchain is not applicable, at least they had a software prototype that they could use. So it was basically a win-win, and we got some funding, which was also nice. So let's speak about how this project was designed. Our preconditions were we need to use blockchains to some extent. And what we also needed to do is we need to put into software this process of transferring energy or kilowatt hours or whatever it was, these proportions, to move them between participants of a particular PV panel. So what we saw right in the beginning, this is a very good case for private permissioned blockchain. Private because usually outside of your group of people who owns this PV, it's not really for anybody else to even see what the distribution is like, because that's a thing that is limited to this apartment or to this house. With them and the energy provider, basically nobody else is supposed to see that or edit that in any way. A permissioned blockchain because you have certain actors that have certain permissions in that chain. So for example, if I'm participant A, of course it should be possible for me to move my proportions to my neighbors. But it should not be possible for me to move my neighbor's portions to me, because today I will consume a lot of electricity. That would not be okay. And in the same way, it should not be okay for the energy provider in any way to edit the proportions, because they are supposed to be a sort of read-only participant. They can register in their system whatever the current state is, what the participants agreed on, and they can use that for billing or any other purpose. But they're not supposed to edit anything. So in this private permission blockchain, all participants are known, because legally, when they register this PV with the energy provider, you need to have a list of people with signatures, so the list of participants is completely known, and the energy provider is known. We don't want to have any outside access from anybody else, and you have no central trusted party. Because I don't know how many of you live in multi-party homes. The trust between parties for certain things is not always the best. At least it's like this in Austria, if it's about to repair the roof or not. Those who live near the roof, they might care a lot, and those who live near the basement, they might not care at all. And there might be a bit of disagreement, and it might be difficult to reach a consensus. So we thought this might be actually an interesting case for blockchain, because you have parties with different interests and they need to come to some agreement, and it should be fast enough that you can, in each 15-minute time slot, to give some information to the energy provider. Also, there is one additional condition. In Austria and most of the European Union, you can choose your energy provider freely. It's not fixed that each participant even has the same energy provider. This makes things potentially very difficult. In our case, fortunately, every participant had actually the same energy provider, so things were a bit easier with the billing law of it. But we wanted to include this for the future in case it was used by anybody else, because in the end it was a research result that we also wanted to publish. As I said, the energy provider has an important role here as a read-only party. The energy provider is not supposed to do any transactions on this blockchain. It's limited to the participants themselves. There were two legal caveats that we needed to address, and they were a bit subtle. So in Austria, as of 2017, as far as I know, it's still the same now, you need a license to trade electricity, which is quite bad because it seems to be being in exact conflict with the law that I just stated, where participants are allowed to trade energy with each other. So, of course, in Austria they did it in a very clever way. They didn't say that you can actually trade energy. They say you can trade portions of the generated electricity. But this is much more difficult to convey to the average consumer, because you don't know yet how much energy will be consumed at 12 o'clock this day, for example. You don't know that. You cannot put a monetary value to it. You can make an estimate, but you don't know for sure how much it will be. And you're also not allowed to brand something like a trading app and put euro values or kilowatt hours in there, because then the regulators will slap you and say you're not allowed to do that. You're not supposed to trade actual electricity. Even though in reality what you're doing, you do trade electricity to some extent. So we needed to keep that in mind when we designed our application, and of course to still give enough information for the people who are using the app, who might not really care how much power is generated. They just want to shift electricity and know how much they're saving through it. So if we want to reach a consensus between the parties, here is a much simpler example. We might have different PV units, we might have different participants, and the most important thing is that at every point in time we have a valid state. So all the participants need to agree on a valid state. If there is, for example, PV number 1 and the users are involved with this PV, they should not have, for example, a distribution that is in any way linked to any excess energy. Or for example, if you have PV number 2, you should have users. They can be connected to multiple PVs, that's perfectly fine. But what can definitely be the case is that any trade is happening that contradicts any of the other trades towards the energy provider. Because the energy provider has 100% of the generated energy, and it needs to assign this energy to the bills of the individual people. So that's what they need to do. So how do we come to a consensus? What is very clear is that the sum of the portions, they must equal 100% exactly. No energy can be lost or just evaporated, that's not possible. And in the same way, you can also not have 110% all of a sudden, because who will pay for that? It's also a very important condition that you can never have any negative proportions of any participant. This might seem obvious, but it's something that is not explicitly stated in the law. So we just defined, together with our energy providers, we defined that it should not be possible that someone transfers more of their portions than they actually have. So this is something that limits the system a little bit, but we thought this was a very practical way of dealing with things, because what would it mean if you have negative energy of any sort, or negative portions?
So it's really physical, if you want, it's a physical.
Yes, of course, again, physically you can do it, yes, of course. But I think it would be quite a pain with billing. Like, hey, on this month's bill you have minus 20% of electricity consumption from your PV. That might be quite difficult to convey to a customer if they accidentally send more than they should actually have sent. There's also one other aspect that the law, as far as we could tell, did not explicitly state, so you can transfer a portion of your PV to your neighbor, for example. It did not say that there should be any consent by the receiving party. So for example, I can say, I give to my neighbor 20%. They have no possibility to refuse, because in the end, there is no negative effect if they don't use it, because it will have the same effect basically if I don't use it or they don't use it, because at the end of the year there will be still a certain tariff that is to be gotten from the electricity provider for the energy, for the excess energy that is put into the grid. That was a bit subtle, and it was not clear at the time if this is something that we could actually do, but since it was a prototype, we tried to do it that way and we saw how it worked. And in the end, if my recipient doesn't want the portions for themselves, they still have the possibility to pass them on to somebody else. And the larger the community is, the easier it is to find somebody else who will be gladly taking some PV portions. So that was the basics of the design for the blockchain itself. We did something where we knew at the time, looking back 5 years later, it might not be a good choice. But it was the best choice at the time, in our opinion, so we decided back then to do a proof of work-based blockchain. Nowadays you would say it would make much more sense to use anything else, proof of authority or whatnot, but back then most of the implementations were not mature enough yet that we could really test them out in the field. So apart from the obvious things like the proof of stake would make no sense whatsoever in that case, we saw that, for example, Byzantine fault tolerance protocols were already maturing, but they were not yet at the point where you could just take one of the implementations and use it in a real-world scenario, because this stuff should work well enough that the energy providers could do a full implementation based on that. Of course, there is the main concern about proof of work about the energy need to achieve the proof of work consensus. So in our case, we had the energy providers on our side, because they said, look, whatever we as energy providers do, we can provide a special hardware device for the customers, and we can make sure that this is sealed and tamper-proof, at least according to the regulations at the time, and we can make sure that we limit the energy consumption of this device, because it wouldn't make a lot of sense to do a 1 kilowatt-hour mining per day operation to save 0.2 kilowatt-hours of energy. So we needed to reduce that quite a lot, and we saw that proof of work would be an intermediate solution that would need replacement certainly a few years down the road, when there would be some other mechanisms that were more mature at the time. So in this case, for the energy provider case, we have this situation that we have tamper-proof hardware, at least tamper-proof enough for the average user and what the regulations require us to do. I put here, just for the sake of completeness, a very small portion of what we later published in a paper to motivate why we're actually using proof of work and what the other solutions would have been at the time. Remember, this was 2017 when the project started, so a lot of things that are now existing did not exist back then, or they were not mature enough to use them in everyday operations. Most notably, one question that popped up, also with the reviewers later, why do you just not modify Bitcoin or Ethereum for your use case? That's true, we could have done that, but we had a very limited time budget, and it appeared to us that it might make a bit more sense to write the most minimalistic version of this ourselves. We had 2 PhD students and 1 postdoc working on it, and we were trying to limit the effort for the proof of work in such a way that only the stuff that we really needed was done at the time, and that the energy consumption was below a threshold that the energy providers thought was feasible for the use case. We had other potential solutions in that time, like Hyperledger was about to become more popular, but it was not at a state to be able to use it for the project itself. That might be different today. But back then, we were a bit limited with our options. So let me show a simplification of the architecture that we had. We had n nodes for every one of the customers. We had a node that was placed in their home. Then there was the blockchain, and every node could perform transactions. The transaction was just moving portions of the PV energy from one participant to the other. And those were in the end confirmed and landing on the blockchain through proof of work. And since a regular user would like to have a nice user interface where they can move the portions around, we had a former student of ours program a little app. And this app should be as easy to use as possible, with a lot of nice pictures, so that it's not too much text, not too much numbers, or any of that, so that the people are incentivized to really trade their energy portions. There was also this nice black box, which is legally required. This is the so-called clearing server. So the clearing server, once per day or once per month, needs to read the state of this blockchain to determine what were the exact proportions of generated energy, how are they distributed in every 15-minute interval between the participants. And then there is some magic billing happening, but that's outside of our ecosystem because that's the energy provider's business. So that was the simplified view onto the architecture. Here is a more complete picture of it. So as these nodes, they are every customer, and these nodes are connected with the app that the customers have, and they can do the transactions between themselves if they're authorized to do so. And what is also possible in this context is to have multiple clearing servers, because we had 2 energy providers in our project. So each of them has a different clearing server with different customers, different billing processes. So it's very important that both of them get access to read from the blockchain in such a way that they can do their billing accordingly with only their customers. There was also this privacy issue of what would the other energy provider do to not read the transactions or the state of the first customer. A bit ironically, our research center is very much focused on privacy and security, but for this particular case, since the energy providers were working together, it was only a proof of concept with very little time, we decided to skip this step and see that the clearing servers were only reading their respective parts. This is something that was not optimal, of course. We would do that differently if we were to do it again. But it's something that we saw no one in the group of customers or energy providers was really concerned about. So this is something that for a future project we would certainly consider. We'll talk a little bit about the implementation details and then afterwards some interesting conclusions that we got from this project. So for the implementation, we decided to use a Raspberry Pi because it was easily available, it was very small, and you could put it very easily into a customer's home. It can run Linux, which is a big plus because it means that you can run a lot of off-the-shelf software there. And it has by itself a relatively low energy consumption because it doesn't have much to do. We don't use any fancy I/O stuff, we just use networking. And the other thing we use is to do some proof of work, but very resource limited so that the energy consumption is not too high. We decided to implement the most basic version of a blockchain ourselves. Also, that is something that we would do differently now, but back then, as I said, the options that were available to us in the time frame that we had were not such that we would say, let's just use this implementation and change it, because that would have taken much more time. We decided to implement this in Java. One reason was because the main PhD student who was working on the project liked Java very much. But of course, this also was due to the fact that a lot of functionality regarding network traffic, network interfacing, cryptographic functionality, all of that was already included. You have things like concurrent data structures, which allow you to very easily do things without needing to implement it yourself, and you know that these standard library functions are well tested and well behaved. We put our chain as open source online, so feel free to have a look at it or use it if you like. This is something that we found to be very helpful. We had other company partners who wanted to build on it. Not that I necessarily recommend to build your real-world use case on just that implementation. It might not be perfect for your use case, might not be perfect in general, but it's something that you can see to maybe get an intuition what you could do and which design decisions to make. In addition, we had the customer app. It was Android-based. Since we had a bit of hardware budget in our project, we could buy nice little tablets for the end users, which we could give to them. And They were all running Android, so we didn't need to bother to make two apps, one for Android and one for iOS. So we could just make this app and have it pre-installed on the tablets for all the users, and we gave them some initial instructions when we handed over the tablets. So we showed them how this works, so that they gave extra instructions for them so that they were motivated to use it. Our actual implementation of this piece of Java software was like this, that we had connections to the other peers open, so every one of our nodes was connected to all of the other nodes because it was a very small network. I will talk about this in a minute, why we need to have so many connections open and why we need a connection watchdog for any of the connections. This is one of the very surprising things that we found later on. And whenever there is an entry being done through the app, it lands on the node of the device that is at this customer's home. The entry is processed, it's either mined directly or it's just appended and sent out to the other clients. And the mining that is going on is very similar to how mining looks in Bitcoin. The only difference is that the difficulty of the mining is always limited to the same value and all the devices are running at the same speed. We have two data structures here. One is a state table that gives an overview of what the current state of these 15-minute values is. And the second thing is a tree-like structure that basically represents the blockchain itself. So that at any time, if another block comes along, the longest chain is no longer the longest chain, we can do some shuffling around and to still recompute the current values. This is also important because from any node, the energy provider should be able to read the state and to see what are, for example, for the time of this lecture, what are the time slots where the proportions are like this and this at 11 o'clock, so that we can read it directly. So it's an easier way to get access to this. The network setup was a bit tricky because we couldn't use power line communication. So we relied on our users being power users and giving us internet access because they were very friendly and they were very motivated to participate in the project. And of course, this is regular public internet in Austria, so it might be that every 2 hours you get a new IP address. It might be that you have 1, 2, or even 3 devices between network address translation of any sort. So we installed on the Raspberry Pis and on the tablets some VPN software where we established a small virtual private network to enable the devices to communicate with one another even if they were behind some network address translation. Because we could not bother the customers with configuring their network in such a way that everything would work out of the box. We wanted that to be as easy as possible for the customers. Keep in mind those were power users. If you do that with a regular user, this becomes even more important because they might not even know what kind of internet access they have. As I said, the customer app is connected to the node in the home of the customer, so they can do the transactions directly. And the app also represents the current state, so if somebody is sending them portions from their PV, it will show up in the app so that they have a visual representation that they now have more portions of the PV for a certain amount of time. We used mainly XML over TCP/IP for the nodes, and for the clearing server to read the data, we used mainly HTTPS. We did a REST interface that was easy enough to just read 15-minute values for a certain PV out of that. So at this level, of course, in case you want to add some access control, you could, for example, use a bearer token or anything you like, so that only the energy provider who's authorized to really read that data is allowed to use that data. In terms of security, we had pre-distributed public-private key pairs, so there was a public-private key pair for each of the nodes, so all the participants are known in advance. Our study was very limited in time. If you do this in the real world, you need to consider that there might be participants joining or leaving. Let's say someone sells their apartment and moves away. They should no longer have access or any rights to transfer portions, but the new person that moves in might need to. All of our transactions are signed, so the people who are actually doing the transfer, they authenticate the transactions by signing it with their private key, so everybody else can check with the corresponding public key that the transaction was actually done by the authorized customer who's associated with their portion. All of the connections, even though we were using a VPN already, we still did encrypted connections. We used TLS. We did, in case anybody cares for the details in this case, We used mostly elliptic curve Diffie-Hellman key exchange, ephemeral version, because we were very focused on explaining to our company partners what, for example, does perfect forward secrecy mean. They wanted to learn a bit about blockchain, they wanted to learn a bit about security. So it was nice to add those details in to show them that whatever is going on, even if the layer underneath is compromised in some way, that at least the data and transport is secure enough, even though for this use case it might be overdoing it a bit. Also for the connections themselves, we used AES with 256 bits, because we said rather to be safe than sorry, so just to make sure that we're on the higher end of the key length in this case. So that was the implementation. I will show you a small screenshot of the user interface. We had a very talented UX student who did that. The customers were very happy with the application because it basically showed you in different resolutions the whole day. You could scroll left and right like in a calendar, and it would show you usually when it's sunny. So for example, at 8 o'clock or at 12 o'clock, it will be sunny. And during the night, it will show a moon symbol, where you could still transfer portions around, but it gave you immediate visual feedback that there might be nothing to transfer. Because at night, the PV might not have any significant portion of energy generation. What you could do is you could take one of those sun symbols and you could drag them down. And when you're dragging them down, it would show on a circle how much you're transferring. And we decided that from your own portion that you have, however much that might be, we give certain percentages, 10, 20, 30, 40 of the percentage that you already have, because it's easier than to show the actual percentages all the time, because people usually don't care and it's a bit too complex to visualize them. So you could drag this down and you decide to send this. Here you can see an example of when the transactions have been performed, and the user has, for example, sent a little bit more than half of their portions to somebody else. You could click on that and you could see it, and that is something, as long as it's in the future, you could even cancel it, but as soon as it was in the past, there was no longer the possibility to undo what you've done, because you need to agree up to the certain point on the state that everybody agrees on. We also had a lot of features for the user to see how much they save. We added some little information about how many kilowatt hours that might be, based on the weather forecast and based on the actual PVs. We got some information from the energy provider about that, because the power users were interested, like how much do I save when I do that? We also displayed a euro amount, but we needed to do that in a way that was a little bit more hidden, so it's obvious enough for the user, but that the regulators don't tell us, hey, please don't do that. Because it's still something, they don't have energy trading licenses, so we're not legally allowed to trade actual energy, even though that's in effect what we did. How did the proof of concept look like? We had two locations in Austria, one was in Salzburg and one was close to Vienna. And we were working with two energy providers, and unfortunately, as it always is with projects that have a limited scope and time, until all the customers are enrolled, until all the installations on the electrical side are done, until all the agreements are in contracts, the number of participants constantly decreases until the start of the actual project. So in the end, we were only operating in one single location with the customers, because the other location, unfortunately, took a bit too much time to get started. But still, we wanted to get the results out. And we had a trial throughout the second half of 2018. So we started around June, and it ended towards November, so it was about half a year of data that we would collect. And we had nodes at each customer's home, of course. We had nodes at both of the energy providers, so even though the second energy provider didn't have any actual customers that were using the system, we still had a node at their place because they were part of the project, and we wanted also to see how this thing works across longer distances, like 300 kilometers apart. It's not big, but we thought it might be interesting in case the internet drops out or the nodes have connection issues, like how this would work over such distances. We also had some nodes at our university. Officially, of course, for mining and reading only. In reality, of course, there was a certain debugging aspect to it, because of course we tested all the stuff. But if it's out in the field for half a year, it's quite a different story. So we wanted to make sure if anything bad happens that we have some nodes also at our university to see if anything on the blockchain goes horribly wrong. Fortunately, it didn't. The students implemented the system very nicely and it was running very stable, so that was very good. But still we wanted to keep our options open for that, since it was only proof of concept. Now we'll come to the final part of the presentation. What were the lessons learned from all of that? And some of this might be super obvious, I'm aware of that, but it's still something that I think that in Austria we were the first that did a prototype like this, so we wanted to share this experience, and we also wrote a paper about it to share our experience with others so that they hopefully can improve their designs based on some of the design decisions that we maybe did in error or that we maybe did in a suboptimal way. One of the first and most obvious lessons was, of course, proof of work is not the best way to do things. It was maybe back then, but nowadays we would maybe use Byzantine fault tolerance protocols. They're now mature enough, in our opinion, that you can use them even for bigger setups. I mean, the average household in Austria, the apartment houses, something like 10 or 12 apartments, so that's quite okay still. If you have real apartment complexes with 20 stories with 1,000 people living in there, it's different. But still, for these cases, it might be quite good to use Byzantine fault tolerance protocols. Also because the scalability is better, they use much less energy because you don't do any sort of mining in that sense. You just need to come to a consensus. We also found what was quite interesting to us, that our TLS connections added a quite significant delay, not only between between Salzburg and Vienna, but also when we did local testing. Because as you might imagine, when you first implement such a thing, you test it with no encryption and you test it in your local network because you want it to work there before you put it out somewhere where the settings are a bit more challenging. So what we found that when we switched to encrypted connections, that we had a lot of very interesting delays, and these were mostly happening during the key exchange phase, because remember we were using Diffie-Hellman ephemerals. We were establishing a new key for each connection that we were making. Even though we tried to keep the connections open, that meant every time the key was renegotiated, you go through the whole process of doing this on a piece of hardware that is maybe not the most powerful by design. So what we needed to do we needed to put much higher timeouts than we expected to be, and I will show you a small figure of the delays that we measured in our local network. This was not between Salzburg and Vienna, this was in our local network. When you see if you open a regular unencrypted socket, the median value that you have is approximately 5 milliseconds to send the smallest amount of data, like some dummy byte of data. While if you use a TLS-based socket, we found that you're about 2.5 times of the delay, and that might have quite an impact if there are a lot of transactions in your network, or if you lose your connections frequently. You see that the outliers are not so different between the two, so you can see that we had outliers of up to nearly 30 milliseconds in the unencrypted case. That's not so different from the encrypted case, but it's still something that the median value is so far apart that your average connection speed is just slowed down by this a little bit. And since our transactions are very small, how much payload is there? You need a sender, recipient, percentage, and then you need to sign the whole thing. There's not much more to it. So the overhead is quite significant for this kind of payload. Some more lessons learned. This was purely our fault because we were not reading the documentation in the beginning to the extent that we should have. Most of you might know, if you use Java 8 out of the box because of the US export restrictions, AES 256 is disabled. Disabled means if you try to invoke it, you'll get a super nice exception and nothing works. So you have two choices. You either can limit AES to 128 bits as a fallback, or you have two solutions to actually go around the export restrictions, because Austria apparently is not the US, so we are not really concerned about these export restrictions. So there is an official way. The official way is not very nice because it requires you, with every single software update that you do, to place in a certain system-wide folder some files that indicate to the Java runtime that it's allowed to use the stronger version of encryption. That's not nice because if you want to do any remote updates, you don't want to need root permissions for that. That's usually not good. And we didn't want to make our own updater software just in case something breaks, because if you have an updater running, that you wrote on your own, that has root permissions, it's maybe not a good idea to do that, if you can avoid it. And the second way that we ended up using was an unofficial way that was clear it could break at any moment with the next software update, but it was very nice because you didn't need to install any files anywhere. And that was through Java reflection. You could effectively set some internal state bits. There was plenty of code out there on the internet that you can use, plenty of different ways to achieve the same thing. It worked then, but it was something that we didn't expect because we were very much focused on getting secure connections, and we were very surprised when what was working on our dev machine suddenly didn't work on the freshly set up Raspberry Pis. Because of course, if you set this up on your own computer, of course you put the files where they should be, and you might forget about it, and then later when you deploy it, you find out, I should have put the files there. And that's something that we learned from there, which was a bit unexpected. What was also unexpected is if you use networking threads, and you have a thread who is talking to the other nodes of your network, and your TLS connection for some reason drops out, times out, or anything bad happens to it, what might happen is that your thread is infinitely waiting for that until the timeout is reached. So the timeout, once it gets in place, you might miss a lot of other stuff that is happening on the other node. So the logical conclusion was you just open one single thread and one single socket to talk to each of the nodes. But even then we found that if you do that and you have a very shaky network, which we nicely simulated by plugging and unplugging the Ethernet cables of our Raspberry Pis, what we found out was that if you find the right circumstances, it can still be that you're not able to get your transactions out because your Raspberry Pi is so busy renegotiating all the connections to the dropped out connections that were existing that if your user wanted to send a transaction that was time critical, I want for the next 15 minutes to send my portion to my neighbor, it might not be able to get out because all the sockets are blocked or are in a state where they're waiting for something. So this we solved by just adding another communication thread that was purely for sending transactions out. And in the final version, we even had connection watchdogs where we did connections to each of the neighboring nodes, sending and receiving. So if we had 10 nodes in the network, we had 20 threads open, sending and receiving to make sure that at least to some of the nodes our transaction gets out. What might also be obvious if you write your own blockchain, by the way, don't write your own blockchain if you don't need to. Resynchronization is really, really hard. So the students struggled quite a lot to implement that. I was also having some fun debugging some of these things. You can get into some very strange conditions in places where you don't expect it. You can have blocks missing of any type. For example, if you lose your network connection for 1 hour and a lot of transactions happen during that time, let's say your blockchain is at block number 20, and then when your connection comes back on, you get block number 1005, 1006, 1007. The problem is, what do you do with them? You have no real way to append them to your chain in any valid way, so you need to request from your neighboring nodes whatever they have to build a valid chain. And that's quite a pain to implement. So that's something I don't recommend that anybody would try to do. There are people who are really experts in that. I don't count myself among them. With our implementation, it did work in all of the scenarios we tested, but it's still certainly not at the level where it should be to be an actual implementation that's super stable against all sorts of border conditions. One of the most surprising security implications that we found were what happens in a proof-of-work blockchain if you don't have any transactions. Let's imagine you have your 10 participants, it's 2 o'clock at night, nobody's trading any electricity, nobody's trading any portions of their PV. What do? You have 2 options. Either you can say, I don't care, there are no transactions, so it's no problem. Even though it is a problem, because if there were an attacker, it would give them a lot of time to pre-mine another set of blocks that are to their advantage to some extent. Or you could also, in some regard, as a single user, if you had a vested interest in that, even with the sealed hardware, you could try to pre-mine blocks for yourself that benefit you. So the other option that you have is that you just say, I allow empty blocks to exist. I just say, okay, there are no transactions at the moment. We still have our predefined mining speed, and we just put no transactions in our block. Just 0 transactions at this point. This is a problem that Bitcoin doesn't have, because there's always someone who wants to send Bitcoin from one address to the next. It was a big problem in our solution. It was also surprising for our company partners, the energy providers, to see that blockchains exist where one of your biggest issues on the security side might be that you run out of transactions, because there are not enough, especially in a small network. If you do this Austria-wide, it might not be that much of an issue, but if you do it locally, it might be quite a big of an issue. One last set of lessons learned from this. There is this whole thing of user engagement. As I said, we have power users. So those users were super interested to see what happens. They wanted to learn about the cost savings. They wanted to have some detailed insights. We even gave them an app to explore the blockchain a bit, to explain to them what a blockchain was and what it's useful for. And they found all of that very interesting, and they were very active in trading in the beginning. And then it stopped. And we were trying to find out why it stopped. Why are the people not making any more transactions? And our sample was very small, so I don't try to generalize this here, because this might be the isolated opinion of a few power user Austrians who have this opinion about our particular proof of concept. So, on the one hand, even though we displayed the kilowatt hours, at least estimated, the kilowatt hours and the amounts in euros, those are still usually very small. If I own, say, 20% of the PV and I send half of it to my neighbor, for 1 hour we're talking even about a few euro cents. So that's something that's usually not appealing enough to fire up my app and then to play around with it. So that's a component that should be considered. It was also that the users knew that you could not transfer any actual euros, you could not transfer any actual kilowatt hours. And that's a big issue, because you can only transfer portions, and it seemed that this got a bit boring over time. Because you could not send an amount in euros, even though you would see that the amount in euros would be approximately this and that. But still, you could only send the portions. And finally, it seemed that the incentive to send PV portions to somebody else, which is more altruistic than egoistic, is something that might not have enough of an incentive, again, to fire up the tablet and play around with that. This is something that's outside of my area of expertise, so I would be very interested also to hear from people who are more versed in psychology and the aspects of human behavior in this case. If you decide to send portions to other people, how they react to that and what that does with you, and how to keep users engaged to keep doing that. I don't know the answer to that, but I know from our proof of concept, if we were contacting the users and asked them, hey, how's it going with the transfers, you will see after a period of no transactions a sudden spike. They were using the app again, and then it would slow down quite quickly. One final remark, one final lesson learned. You might imagine that the energy providers were not very happy about this law that required them to really have 50-minute resolution shifts and to consider all of that in their billing. So it seemed that, to their benefit, the law changed very briefly after our project ended. And the new law is basically now the same as the old law, only that for every single change that is done, the energy provider can charge. So it's possible for the energy provider in Austria to say, that's nice if you want to change your distribution of proportions, but here is a fee because I have some effort to put this into my system. Of course, the incentive not to do that is even lower. There's even less of an incentive to have people trade their portions, because every single time they change their portions, they need to weigh if it's even worth the effort in a monetary sense if they pay the processing fee by the energy provider in order to do what they want to do in order to save a little bit of money. So that's something that's maybe one of the most interesting findings, because this made basically our project obsolete to some extent, but still our lessons learned, we were able to publish them in this paper. It has a lot more details than I could put in a 1-hour talk, but I think it might still be quite interesting to see the various aspects, also legal aspects and the aspects of user behavior. And that brings me to the end of my presentation, where I want to thank not only the PhD students who are working on that, but of course also our company partners who are very much involved and helped us a lot in doing all of these great things and allowing us to do the actual implementation in the field with some real users, even though it were a bit fewer than we wanted them to be, but I hope that still I could give you some insights and could share some interesting conclusions with you. Thank you.